So I'm just sharing the schedule. So we have 4 papers in the session, and we're waiting. I think still waiting for the 4th author or presenter.
Good morning, ladies and gentlemen. My name is Mohamed-Ahmed. I will present the topic of the
Yeah, the sound is low. Can you increase the volume?
with obstacle avoidance. This paper prepared by Mohamed-Ahmed and Aziz Norman.
What about now?
University, the
I think
Laboratory
it's
of
good.
and Systems. This presentation is divided. Good morning, ladies and gentlemen. My name is Mohamed.
Okay, I think we're ready to start. Hello, everybody. Good morning or good evening to Thomas from Chile. As he informed me, it's what, 4 a.m.
Yes, it is. It is. Good morning.
Us, and hopefully you can find the energy to answer some questions at the end. So welcome to the session. It's a session on modeling of control applications. It's a session that hosts the 4 papers that we got for IMAACA. And we thank all the authors that got the time to write their work and prepare all the required information for the conference. It's a pity that we cannot meet in person, and hopefully we'll be able to do better next year. So with that, we can start with the first paper. It's called Decentralized Navigation Control of Multiple Vehicles with Obstacle Avoidance. And it's coming from France, from the University of Marseille and Toulon. And it's going to be presented by the first author of the paper, Dr. Mohamed-Ahmed. So can we start the video? And then, just a second, please. We're gonna play the video, and then at the end we're gonna have time for questions by the audience. So let's start the video, please.
Ahmed, I will present a solution decentralized navigation control of multiple vehicles with obstacle avoidance. This paper prepared by Mohamed-Ahmed and Aziz Norman, next Marseille University, the Laboratory of the Computer and Systems. This presentation is divided into introduction, modeling, longitudinal control, lateral control, validation, party, and conclusion. To introduce, the aim of this presentation is to propose the longitudinal control, for example, to answer the stability and to follow the reference speed of the leader and to avoid the collision between the vehicle. For this, we use.
Mohamed, can you also turn your camera, please?
For the lateral movement, the convoy is controlled to avoid the obstacle. This obstacle can be mobile or immobile in the same trajectory when we have the other vehicle in the trajectory multi-line or the one line. For the modeling parts here, we have the description of the vehicle. For example, this represents the longitudinal movement, lateral movement, and the yaw movement. Gx represents the displacement of the longitudinal, Gy for the lateral, and here we have the 2 repairs, the reference repair and the repair of the vehicle. To present the state model of the convoy, we have the Z represents the state vector. For example, Z1 and Z2. Z1 represents the 3 position and Z2 represents the 3 speed of the convoy. For example, here we have the state model of the convoy for the nonlinear systems. F and G is defined here. For example, this represents the inertial matrix and this represents the vector, represents the dynamic, the nonlinear dynamic of the convoy. Here we have the input for the ECM vehicle. We have 3 for the longitudinal, lateral, and serial movement. For the longitudinal, we control the convoy by the torque, and for the lateral movement, we control the convoy by the steering angle. The aim of the longitudinal control of the convoy is to follow the speed of the leader. For example, here we use the global decentralization approach. We assume we have the information of the leader and the neighbor vehicle to control the longitudinal movement of the vehicle. Firstly, we define the error between neighbors vehicle, for example, between the ECM and E-1 vehicle. Here, S is represents the curvilinear abscissa and for the ECM vehicle, and here for the E-10 vehicle or the preceding vehicle. LT represents the safety distance to avoid the collision between the vehicle. Here we have the two error of speed, the error speed between the neighbor vehicle and between the ECM and the leader vehicle. To control the longitudinal movement, we use the linearization control by inverse dynamics based on the global decentralization approach for the longitudinal movement. This represents the expression of this control. We have the 3 to follow the reference of the leader and the neighbor vehicle, for example, here, and this represents the mass of the longitudinal movement, the mass of the vehicle, and beta represents the longitudinal dynamic of the ECM vehicle, because we control the longitudinal movement of the L vehicle. To answer the stability, we use the Lyapunov approach. For example, here the X represents the Lyapunov function candidate based on the speed, speed error and the position error, and we derive this function to answer the stability. For example, here the dot is negative, so we can answer the stability in closed loop. For the lateral control or the lateral movement of the vehicle, we have the 2 aims. For example, here we generalize the trajectory to avoid the obstacle. Here, for example, this is the obstacle. This is the longitudinal safety between the convoy and the obstacle. Here we have the present position of passage to attain or to generate the obstacle avoidance maneuver. Here, for example, can maybe the next line represent the slope of the sigmoid function. So here we have the sigmoid function to generate the trajectory to avoid the obstacle. This obstacle can be mobile or immobile. So the R vehicle controlled to avoid this obstacle and to return in the reference trajectory. For this, when we generate the trajectory, we use the sliding mode control to follow the trajectory generated by the sigmoid function. For example, when we use the sliding control, we have two parts. The sin function, the robustness party of the sliding mode control. We have the 2 parts, the equivalent control and the sliding robustness control based on the sin function. And to study the stability, we can use the Lyapunov function based on the sliding surface to answer the stability for the lateral movement. So we have to generate the trajectory and to follow the trajectory generated by the sigmoid function. The validation of the difference approach, we use the Scanner Studio. The Scanner Studio, we coupled with the MATLAB Simulink, so we can control the convoy to follow the trajectory. We can control the convoy in real time to avoid the obstacle. We have 2 scenarios. The first scenario, the obstacle is immobile. Here we have the initial position of all vehicles, the convoy, and the initial position of the obstacle. the speed of obstacle equals 0. So when the vehicle, the convoy arrived on the obstacle, the sigmoid function will be generate the trajectory, and the sliding mode control will be control the convoy to avoid to follow the trajectory generated by the sigmoid function. So when after the all vehicle control to return on the reference trajectory. Here we have 3 time equals 0, 12, and 10. Represent the result simulation using the MATLAB and Scanner Studio. We have the longitudinal speed, the distance between the neighbor vehicle 6 meters, and here we have the lateral error, the curvature of the trajectory. Here we have the thrilling angle, the lateral acceleration, the lateral speed, and the yaw rate. For the next scenario, the obstacle is mobile. Here, for example, you have the initial position of the vehicle. Here we have the initial position of the obstacle, and the obstacle moving for the t equal 22 seconds. Here represent the position of the obstacle, and the vehicle will, when arrived on the obstacle, will be avoiding using the trajectory generated by the sigmoid function and the sliding mode control. So we have 3 positions here: the first position, here the second position, and here we have the third position of the vehicle. So the obstacle is vehicle moving with the speed slowly than the speed of the vehicle. So here we have the longitudinal speed of the convoy. For example, the longitudinal speed of the convoy, the longitudinal speed of the obstacle, and here we have the vehicle distance 6 meters. Here we have the lateral error, and here we have the curvature of the trajectory. Here we have the thrilling angle, lateral acceleration, lateral speed, and the yaw rate. To conclude in this presentation, we have proposed the longitudinal and lateral control of the convoy of the many vehicle. For the longitudinal, we have proposed a global decentralization approach using the nonlinear control using the information of the leader and the neighbor vehicle. For the lateral control, we have proposed the sigmoid function to generate the trajectory to avoid the obstacle, and using the sliding mode control to follow the trajectory generated by the sigmoid function. So the convoy is controlled to the vehicle are controlled to avoid this obstacle. This obstacle can be mobile or the immobile. Thank you.
Okay. Now we can. We have time for questions from our audience. Any questions? You don't have to raise your hand, just turn on your microphone and speak, please. Okay, let me start with one question related. Control is always dependent on the dynamic model that you use for, to design the controller. And for a specific case, the tire modeling should be it's a critical part of the model, especially in the lateral direction. So what kind of model did you use for the tire?
Thank you. In this presentation, we have used the dynamic model of the vehicle have 4 wheels. So, for example, we have 3 movements: the longitudinal movement, and the lateral movement, and the yaw movement. So we have 3 movements of the convoy. So we have used the nonlinear models because when we use, for example, the model used in the literature, the double integrator, for example, the model linearization, for example, model linear, we can have the stability in closed loop, or the stability, it's not very robustness. But when we control the all vehicle based on the nonlinear nonlinear description of the vehicle, we can ensure the global stability. So we have used the model very complex to take account the nonlinear dynamic of the all vehicle because this ameliorate the stability and the security of the all vehicle.
Okay.
So for the longitudinal control, for example, we use this to control the longitudinal movement. The vehicle are controlled to use the information of the leader and the neighbor vehicle. For example, we can communicate the vitesse of the leader, the speed of the leader, and the position of the leader. We can use the ultrasound capture to have the interdistance between the ECM and the preceding vehicle. For this, we use the dynamic modeling in the dynamic model to calculate the dynamic inverse in the linearization control and the nonlinear control used for the longitudinal control.
Okay, that sounds good. Also, another hopefully short question is related to the robustness of your controller. And for example, did you study what would be the maximum speed difference of the obstacle?
Yes.
And still have stability?
Yes. In another work, we have studied the stability of the longitudinal control and the lateral control. For example, we can assume in the practical, for example, we have not the all information for the dynamic linear for the dynamic model. For this, we estimate the parameter model. So where your control, for example, the sliding mode control using for the lateral movement, it's robustness command when we have the error in the dynamic model. For example, the parameter, the mass, the constant of the contacts, etc. etc. So the robustness of the controller we have studied in another to aid for example, the error in the parameter, and we have in the another we have aid the error in the capture in the sensor between the vehicle. For example, the information we have the information of the leader. We aid the error to. Hello.
Yes, we can hear you.
We add the error in the capture to test the robustness and to compare the difference approach. For example, we have the difference approach. We can use the information just for example the leader follower. So for this, when you have the error, this error will be accumulated to the other vehicle. For example, so this it's not good for your control. The distance between the vehicle will be more, and when we add the information, for example, the decentralization, you can avoid this problem, for example.
Okay, thank you. Any other questions? Okay, thank you again for the nice presentation and the nice work. And now we can. Mohammed.
We have a question.
Yeah, so, it's just like a technical intervention. Actually, I have just a small technical issue that I think that I have to solve. So I would like to ask the next presenter to present his work, if it's possible.
I have the video, so I'll play the videos.
Okay, thank you for that.
No problem. Okay, we can move on to the next paper, and I would like the next speaker to turn on their camera. So the next paper is titled "A Novel Approach to Handle Intransitive Judgments in Industrial Control Problems," and it's coming from the Czech Republic, and it's going to be presented by Silvia Carpitella, who is currently a postdoctoral research at the Department of Decision-Making Theory at the Institute of Information Theory and Automation at the Czech Academy of Science from the Czech Republic. So let me get the video started. Let's see this one, and hopefully it will work. Share video. Oops, so I have to, let me do it again, because I have to use the sound, include sound. Oh, I decided to install something, so give me a minute. And we want this video. So can you see the video now?
Yes, we can.
Okay, let me start it. So let's watch the video first, the presentation, and then we can have Silvia answer some questions.
This work of research is titled The Novel Approach to Handle Intransitive Judgments in Industrial Control Problems. In particular, we aim to propose a novel methodological approach to support decision-making processes without the need of checking consistency of human judgments previously attributed by decision makers familiar with the field of reference. And to demonstrate the applicability and the effectiveness of our approach, we are going to apply it to a real problem of risk management in a real-world industrial context. In particular, after a brief introduction and literature review, we are going to quickly set the main problem of interest, to then present our approach capable to deal with the inconsistency of judgments. Then we are going to discuss and solve a real-world case study to eventually conclude our presentation. To begin with the introduction, we can consider it as divided into three main areas. First of all, the importance of expert assistance for solving complex business decision-making problems. Then, of course, the fundamental issue of inconsistency affecting the human evaluations. And at the end, the importance of the literature contributions to support our research. Making reliable decisions on relevant business problems often requires the help of experts or decision makers familiar with the field under analysis. In this context,
Professor, I'm afraid the audio has been switched off.
I can hear it.
Yeah, now it's fine.
Oh, so I have, okay, sorry, it was my mistake.
To represent practical business problems, even if they can be potentially not transitive. In this direction, our methodological approach does not require to check consistency of opinions, so that the manipulation of original evaluations can be avoided. This slide just reports a few literature contributions that were useful when developing our research. And now we are going to quickly set the main problem of interest. The analytic hierarchy process is a very well-known multi-criteria decision-making methodology. It is aimed at ranking a set of alternatives, and in particular, this is done by first decomposing the problem into different levels of a hierarchy structure. Each element belonging to the same level of the structure needs to be always compared with elements of the same level with respect to each element that are on the immediately upper level of the same structure. A Actually, comparisons are numerically translated by means of dedicated scales, such as, for instance, the 9-point scale proposed by Tomás. And then all these numerical evaluations are going to be collected in the so-called pairwise comparison matrices. An example is reported in the right side of this slide. Matrices have, of course, to respond to some mathematical properties. First of all, they are, of course, positive matrices, and they have to be homogeneous. It means that each element, when pairwise compared to itself, has associated an evaluation of indifference. Also, matrices have to be reciprocal. It means that it will be necessary to collect just a number of evaluations corresponding to the number of cells laying on over the main diagonal of the matrix. Very important, pairwise comparisons have to be consistent. It means that judgments expressed by experts have to be as much as possible coherent. And consistency is a desirable property that not always reciprocal matrices have. Indeed, the analytic hierarchy process provides a measure of consistency by means of the so-called consistency ratio. The first step consists in calculating the kernel eigenvector of the matrix and, of course, the corresponding eigenvalue. Then we are going to compute the consistency index by using the eigenvalue previously calculated, and eventually we can compute the consistency ratio as shown in this slide. This slide reports the complete process of getting consistency through the linearization process, and in particular, by means of this process, we are going to calculate a matrix that can be defined as perfectly consistent, and it is the closest matrix to the matrix of input. Just to provide a quick numerical example, for a matrix of size 3 per 3, we are going to calculate the logarithmic transformation and the projection orthogonal projection onto a linear subspace. And then, by means of a simple operation of exponential, we will be able to get the final closest consistent matrix. Of course, we have to observe that this matrix is just a synthetic result, and it can be also very different with respect to the original matrix. This is the reason why it is important to establish a feedback-based relationship with the expert that eventually has to agree with the final evaluations. To avoid all these problems, we developed a new approach to deal with inconsistent judgments. In particular, this approach can be summarized by means of 4 different steps. First of all, we are going to build the matrix of pairwise comparison for criteria. Then we are going to build matrices of pairwise comparisons of alternatives with respect to each criteria of the problem. Then we are going to aggregate all these matrices into a single matrix and calculate the logarithmic transformation to eventually obtain the maximal preferred elements, something that's avoid to get a proper final ranking of alternatives. So the first step, for example, as we can see, we are going to pairwise compare criteria with respect to the general goal. Then we are going to pairwise compare alternatives with respect to each criteria. So we will have like a number of matrices that is equal to the number of evaluation criteria involved. Then all these matrices will be integrated into one. The logarithmic transformation will be calculated, and we are going to obtain something that is called the final distribution of preference, calculated as shown in this slide. At the end, we are going to search for the maximal preferred element and evaluate the related pairwise degree of preference in this way. In this way, we are gonna be able to highlight these alternatives that is more likely preferred over all the other ones. And also, by calculating the pairwise degree of preference, we can also understand which degree of intensity these alternatives should be preferred to the other ones. So, case study. We are going to present a case study that deals with the topic of risk management in the food industry. In particular, we aim to prioritize interventions of risk management to guarantee the safety of operators that work with a core subsystem belonging to the packaging plant of a food company. This food company is located in Italy and is deputed to the production and commercialization of marine salt for alimentary use. This slide just reports the main equipment involved in the process as a graphical representation of the subsystem of reference. So, summing up, the decision-making problem has the goal of prioritizing risks interventions aimed at optimizing the performance of the system. We have to deal with 4 evaluation criteria. The vector weight has been established by means of the support of dedicated health expert in the field, and under these weights we are going to proceed with the application of our methodology to select the interventions that should be scheduled with priorities, and in this slide on the right part the list of interventions is provided. So actually these matrices correspond to the evaluation of alternatives under each criterion, and as we can observe, the third and the fourth matrices are not consistent within the limits allowed by the methodology. So we are going to aggregate all these matrices into a single one, then we are going to calculate the matrix of local weights, and then we are going to establish the pairwise degrees of preference and the optimum distribution of the same preference. In this way, our approach suggests to schedule with priority the 6th intervention by increasing the frequency of sanitizing interventions on the machines operating in the core subsystem of interest. To conclude our presentation, we can affirm that our approach, the new approach to deal with problems where transitivity of judgments is not granted, can be applied for the management of complex industrial control problems. We extended the applicability of our process within the framework of the analytic hierarchy process methodology. Also, this approach has been applied to a real-world case study on risk management in the food industry for potentiating system control and human safety by relying on original expert judgments. The following risks management actions have been scheduled, starting with the increasing of frequency of sanitizing interventions. I thank you all for your kind attention.
Okay, that was the end of the presentation. Thank you, Silvia, for the nice presentation. And now we have we'll open the floor to questions. Anybody? It's not 100% my area, I have to admit that, but I think I can hopefully not make fool of myself. Always, you're talking about decisions, and in order to make that decision, you have to use some information. So how is maybe the quality of the information affecting the decision, and how is your approach sensitive to the quality of that information?
Yeah, Professor, thank you for these questions, because this is one of the limits of multi-criteria decision-making methodologies, because of course these techniques are based on the collection of human experience. So actually human judgments are always subjective, and we cannot totally avoid like subjectivity affecting input data. We can manage it. We can try to develop mathematically rigorous tools to actually exploit the knowledge of experts, of stakeholders that are familiar with the problem, and turns in an advantage, of course, to come to a better management of the real decision-making problem of interest. But Actually, as you were mentioning, like the collection of input data is led just by simply interviewing experts and asking them to express evaluations about the preference degree between decision-making elements in pair. So actually what we do is actually involving a single decision maker or also a panel of experts and asking them for opinions about their personal perceptions of phenomena. And actually I think that even if we cannot come to an optimal solution, it's always like good to reach a trade-off between mathematical methodologies and experience in the field, so that we can exploit our scientific method to come to a solution that is practical and reflects what really happens in the practice. I hope to have answered to your question.
Well, no, it's it's always tricky to when you have to deal with humans and their opinion about things. So yeah, that was that answered my question. Okay, do we have any other questions? Okay, thank you, Silvia.
Thank you very much.
And we can now move to the next paper, our third paper. It's going to be presented by Tomás. Tomás, forgive my pronunciation of your last name. Can you please say your last name?
No, it's Tomás Pröschle.
Pröschle.
It's kind of Germany.
Okay, yeah, with the I thought it was not was something different. So can you please turn your camera on if that's possible?
It says that the administrator has disabled the share of videos. I'm not
camera, or even we cannot even. Or maybe
I'm not completely familiarized with Microsoft Teams, so.
So you have, don't you have like a camera symbol somewhere on Teams?
Not at all.
There's a microphone, and then next to it should be a camera.
No, it is only. So to the left of the microphone, it is like a video, but
yeah,
doesn't let me click it.
Maybe maybe you have an issue with your camera. That's okay. We can go ahead with the paper.
Okay. I'm sorry.
Yeah, that's okay. That's
so I'll try to fix it in this meantime.
Well, if you can, fine. If not, that's also fine. So Tomás is, thank Tomás for being with us. It's coming from Chile. It's like 4 a.m. or almost 5 now.
Yes.
So he's gonna talk about the title of the fermentation of glycerol using Clostridium. Oh, chemical terms again. That's not my best. That is a chemical.
That's a microorganism, a bacteria.
Okay, butyricum for the production of Propanediol fed batch bioreactor using advanced controllers. So I guess that's a part I understand. The controller, the chemical part, I'm not so familiar with. He's, as we said, coming from Chile. He's currently a master's student and from the Department of Engineering and Bioprocess, I guess from the university, again, the Pontificia Universidad Católica de Chile. And with that, let me try to start the video. Okay, So we want to share this nice video here. There you go. So can you see the video?
Yes, I'm actually seeing it.
Okay, and then I'll just play the video, and at the end we can have some questions. Okay, let's do that.
Hello everyone, I'm Tomás Pröschle and I'm gonna present fermentation of glycerol using Clostridium butyricum for the production of 1,3 Propanediol in a fed batch bioreactor using advanced controllers with my team, Diego Ábalos, Alejandro Sepúlveda, Francisco Yur, Francisco Ibáñez, and José Ricardo Pérez Correa. The contents of these presentations are glycerol fermentation, bioreactor and control, mathematical model, optimal path, multivariable MPC, results and discussions, and last, conclusions. Glycerol is the main byproduct of the biodiesel industry. This industry growth has generated a dramatic surplus of crude glycerol that can be exploited. Currently, glycerol is used in fermentation process to obtain propanediol using bacteria such as Citrobacter, Enterobacter, and Clostridium. Its production is of high interest for the textile and thermoplastic industry, as it has a wide range of applications as a monomer for polyesters, polyether, polyurethane, and PTT. For glycerol fermentation, we choose Clostridium butyricum because it's a suitable microorganism to produce propanediol. It's a strict anaerobic mesophile strain that can metabolize complex substrates and tolerate high glycerol concentrations. In this table, we present the final concentrations and colorimetric productivity of propanediol reported in the literature. For Carpitella used Clostridium diolis, which achieves a productivity of 1.36. Then Luetal, Nuetal, and Luetal again used a different microorganism, and that can explain the higher productivity of their studies. In this study, we used Clostridium butyricum, the same gem of Clostridium diolis, and we achieve a higher concentration and a higher productivity. For the bioreactor and control, we use a fed batch process with the objective of achieving the maximum concentration of propanediol possible. Given this, there is a necessity to control the temperature and glycerol concentration due to its sensitivity to the culture. We will seek then the optimal trajectories of both states of the reactor to assure the maximum concentration is achieved. For this process, we identify two major disturbances. First one is the variation of the glycerol inlet concentration due to its crude state. Second one is the variation of coolant inlet temperature due to its possible changes in the room temperature by the day and night cycle. Therefore, it's necessary to design a robust control to overcome these disturbances and achieve the objective control. Here we show the pipes and instrumentation diagram. We have a 5-liter reactor with a peristaltic pump for the glycerol feed, there controlling the glycerol concentration on the reactor, and 2 peristaltic pumps for the hot and chill water controlling the temperature of the reactor. Regarding the mathematical model, it's derived from mass and energy balances assuming perfectly agitated bioreactor and jacket, no heat losses to the environment, and constant physical properties for the media. It's based on the models developed by Kaur et al. 2012b and Silva et al. 2015, and adding an innovative factor at temperature dependence for the growth of the bacteria. For the mass balances, we have balances for biomass, substrate, the product, and a byproduct, which is an acid, and a volume because it's a fed batch reactor. Then the energy balances, we have a reactor temperature balance, which takes into account the heat produced by the microorganism in the production of propanediol, then the balance for the jacket temperature, and the coolant flow and coolant temperature because it's a mix of 2 streams. For the constitutive equations, the growth rate takes into account the temperature and the concentration of initiatory compounds, which are substrate, product, and acid. Then there are substrate consumption rate, propanediol production rate, acid production rate, and a dilution rate. With the mathematical model presented, we're going to manipulate these variables, the substrate flow rate, the chill water flow rate, and hot water flow rate to control the states of substrate concentration and temperature of the reactor. In order to maximize the concentration of propanediol in the reactor, the orthogonal collocations of finite elements procedure by Carey and Finlayson was implemented, which allows us to calculate the optimal trajectories for the manipulated variables. This method allows the differential of algebraic equations system to be completely discretized, approximating the control variables and the states via polynomial functions at each time interval. These states are defined as this, with 3 Rodel collocation points were used, 0.15, 0.64, and 1 respectively. Then, we can formulate the dynamic optimization problem, where it is the maximization of the product at the final time, subject to the differential equations and the algebraic equations. This problem was solved using AMPL software. Now that we have the optimum trajectory for all the manipulated variables, we will use them as a reference for the controller. Using the Model Predictive Control toolbox for MATLAB 2021A, we design and tune the controller, which has the next cost functions, where NP and NC are the predictive and control horizon, which were set to 20 and 10 respectively. The minimization problem is the following, where U is the manipulated variable spectrum. Lastly, we simulated this plan on Simulink, and we obtained the following results. Here we observe the optimum trajectory for the concentration of glycerol inside the reactor, and how it's being followed by the NPC. This is produced by the following action of the peristaltic touch. Then, for the temperature control loop, we notice that there is a little overshoot at the beginning. That's because the necessity to increase the temperature from 25 Celsius to 37 Celsius. In spite of this, it follows the set point with precision. The action of the controller is the following, where the temperature is generated by the mix of hot water source and a cold water source. We see how the temperature at the beginning is higher and then how it decreases. Finally, the profile inside the reactor is this, and we can see how we achieve a 75 grams per liter in a total time of 40 hours. Regarding the simulations and the dynamics of the system, the set point is followed with great effectiveness in both control loops, therefore achieving the maximum product possible for this set of parameters. The MPC design is robust and overcomes all the disturbances in the system. The optimal trajectory contained by AMPL is consistent with the behavior of the microorganism, considering all the inhibitory effects, and the temperature control manages to increase the reactor temperature quickly at the beginning to reach the reference and then maintain it with great performance. Finally, for the conclusions of this project, the implemented controller achieves the objective in a robust and efficient way. The maximum concentration reached was 75 grams per liter of Propanediol in 40 hours, and this technique proved to be effective and has a great potential for processes that are well identified, since the orthogonal collocations of finite elements method, along with dynamic optimization, allow us to find the optimal trajectory and use it as a reference. Thank you very much.
Thank you, Tomás. Do we have any questions from the audience? Don't be shy. No?
I think not.
Okay, I'll make a quick one, hopefully. In your controller, did you consider any saturation of the actuators? For example, you had a flow rate.
Yes. Actually, if you can switch to the bomb, where is it the graph?
Which one? This one? No.
No, the coolant pumps. Yes.
Yes. Okay.
There's a flow rate in the first 2 to 3 hours. You can see that there is it is looked at the increase of the coolant flow. It is restricted to a certain value, and that is what mainly for controlling the overshoot at the first hours of the.
See, okay.
Yes.
So that's part of the process.
Yes.
Okay.
Because we start at 25 degrees Celsius and the optimum temperature is like 37. So we need to reach quickly that state of optimality, and if we didn't restrict the hot pump, we got a massive overshoot. So that's the need. Yes.
And that's something you, I mean, that saturation you defined by trial and error, or do you have some?
Yes, that was manually tuned.
Okay. Okay, thank you, Thomas.
Thank you.
Any other questions? Okay. Now let's, we can move to the fourth paper. Is the author or the presenter of the fourth paper here? Because at the beginning.
Yes, I am here.
Okay, good. So we can move. Let me get ready here with the video. We have a video, right?
Yes.
Yes, we do have a video. And we have the presenter. So can you please turn your camera on while we play the video and introduce you?
Yes, I try to put my camera, but it does not work. I don't know why.
Not working. Well, maybe the internet doesn't want you to be seen. I don't know.
So.
Okay. So our next paper is titled Synthesis of Petri Nets-based controllers for automation of train routing in a railway node. Nice. The paper comes from the well, it's going to be presented by Professor Armand Toguyéni. I don't know if I said that good enough.
Yes, it's good.
Good enough. Okay, and he comes from the Central Institute and the Crystal Laboratory. He's a full professor in the industrial computer science in Central Lille in France. He's doing research under the Crystal Laboratory, and his research interests are in fault-tolerant control and diagnosis. And his main areas, railway systems, manufacturing systems, and computer networks.
Exactly.
So with that, if you want to add something more, feel free. But with that, we can start the video.
Yes.
And then at the end, we can have some questions. So let me start the video.
Okay.
That.
I switch off my micro.
So can you see the video now?
Yes, it's okay.
So I'll start it, and then in 12.5 minutes we can have questions.
The study deals with the automations of train routing in railway nodes. This work has been carried out at Crystal Laboratory in France. The problematic that we are addressing is to guarantee traffic fluidity in railway nodes. Railway nodes are dense areas such as train stations. They are subjected to congestion. To solve this problem, the study proposed the automations of rail control. But the controller must guarantee that there can be no collisions between the trains inside the node. In the framework of Petri Nets, this can be based on the technique of generalized mutual exclusion constraints that allow bad state avoidance. In these presentations, I will first introduce state avoidance principles and S4PR, a class of generalized Petri nets. Then I will present a new technique for constraint transformations in order to obtain admissible constraints to apply state avoidance based on multiple places in the context of partial observability and controllability. After that, I will apply the obtained result to a railway use case. In the frameworks of Petri Nets, state avoidance can be obtained by the technique of generalized mutual exclusion constraints. A GMAC is a linear constraint that defines the local state in the space of reachable state of the initial model. This linear constraints define the limit number of tokens that can be reached in a subset of places in the model. The vector W define the limit for each place to the forms of a monitor place, the limit for each place with respect to an absolute limit B. When the constraint is admissible, it can be translated into the form of a monitor place that will control the crossing of some transitions of the models. Assume we want to limit the number of tokens in place P2 and P3 to 1 tokens given by the constraint given by these equations. We obtain this value for W and this value for B. So we can generate the monitor place PV that controls the firing of transitions T1 and T2. Let's now introduce the definitions of S-cat pair. S-cat pair for pair is composed by a set of process nets and resource places. In this figure, we have two process nets, one which places are indexed by E, and the other which places are indexed by D. In these examples, we have three monitor places noted PV1, PV2, and PV3 that limits the number of tokens in some of the places. If we consider the case of monitor place PV2, we can see that this place forms an invariance with the process places PA5, PA6, and PB and PB2. In fact, in highway systems, some events cannot be observed or some events cannot be controlled. In Petri Nets model of such systems, we distinguish three types of transitions: controllable transitions that we will represent in blue, uncontrollable but observable transitions that we will represent in red, and uncontrollable and unobservable transitions that we represent in white. From the controls theory, it's not admissible for a monitor place to control uncontrollable transitions. And it's not admissible also for a control place to control unobservable transitions and also to observe the firing of unobservable transitions. If we consider these examples, we can see that we have an arc from place PV2 to transition TB2. This is forbidden, and also that you have an arc from transition TH5 to place PV2. This is also forbidden. We say that the constraint is not admissible. When constraints are not admissible, we can perform transformations of the constraints to obtain constraints that are admissible. When a constraint is not admissible from the control point of view, the idea is to move back the first controllable transitions, the arc linking monitor place to uncontrolled positions. For example, if you consider in the figure the case of PV2, we have an arc from PV2 to TB2, but TB2 is uncontrollable transitions. So the idea is to move this arc to TB1, who is a controllable transitions. Similarly, if a constraint is not admissible from the observability point of view, it is necessary to move the arc linking the unobservable transitions to the monitor place. This arc must be moved to the first controllable transitions on the path from the uncontrollable transition to the same transition of the process. This is required to propagate the constraints to all the path places. This is the role of the FO functions. In our illustrative function, we have three unobservable transitions. If you consider again the case of PV2, we can see that we have this arc that connects the TA5 that is not observable to PV2. So we have to move this arc to TA6. But in this case, we can see that it's necessary to add a new arc from PV2 to TA4. But TA4 is not a controllable transition. So this shows that the solving of one constraint can imply problems to another transitions. So therefore, solving a not admissible constraint can result in a new not admissible constraint. It is therefore necessary to iteratively use the function fc and fo until we have a propagations of constraint to the different spaces of the models, which allow to respect both the controllability and observability constraint. This is the role of the FCO algorithm. Now apply the previous theory to the synthesis of controller for the automated control of railway networks. In this study, we are focused to solve the collisions avoidance problems. A railway system can be broken down into elementary components such as junction and switches. To each component, we can associate a generic Petri Nets models. Thus, the resulting model of a system is obtained by concatenating the models of the different components that compose the systems. Various instruments are placed on the track in order to locate the trends and to transmit the authorizations of movements, allowing them to advance. When a track has two directions, the instrumentation must be doubled in order to adapt it to each direction of traffic. A crossing characterizes the set of routes originating from a single entry into a railway node. To model a railway node, it is necessary to model each crossing in the form of a Petri net by collecting the elementary models of the components of the systems. In the study, we can distinguish two crossings, gamma 1 represented in red and gamma 2 represented in blue. Each of these crossings has a corresponding Petri nets. Separate modeling of crossing can lead to collisions between trends at the level of the component used by each crossing. In order to avoid collision, it is necessary to define the constraint for each component. Here, in these tables, we have each component of the system, and for each component, based on the models of the two crossings, we define the constraints with the name of the places that are constrained by the constraints. But some of the, since the instrumentation present in the infrastructure leads to the presence of unobservable transitions and uncontrollable transitions, it is necessary to transform some constraints to make them admissible. So the third column of the table shows the admissible constraints. The transformations of constraints lead to the constraints of some components being equivalent. For example, the constraints of S6, SW2 and SW3 are equivalent, so we can suppress two of them. Finally, we obtain 8 constraints, and this 8 of constraints give us 8 resources that avoid collisions in the systems. To conclude, we have proposed in this study a method for the generation of monitor places in Carpitella under partial observability and constraints. This allows to model a controller to control strength in a railway node. But some deadlocks can occur in this model, so it is necessary to develop an efficient algorithm to solve deadlocks in these models. And in the future, we want also to propose computer tools to allow engineers to implement it from the layer descriptions of our items. Thank you for your attention.
Thank you. And now we can try to entertain some questions from the audience. If we have some. Anybody, just turn your microphone on and please talk. We're not very crowded. I don't see any action. Armand, how about you said that in order to implement your approach, you need actually in the example, like instrumentation or sensors are installed.
Mm-hmm.
Do you need the speed of trains in that instrumentation, or no?
No. It's not. It's not. The problem is not the speed of the trains. In fact, when the train advance on the stations in the node, we don't have everywhere. We don't have some sensor to detect the presence of the trains. Normally, the trains have to in actual standard, in actual European standard, the trains has to give these locations very frequently, but it depends of the instrumentation. Today, the instrumentation is some things that you have in the infrastructure, in the rail infrastructure, that is called European bellies. With the European bellies, we can just know, not very often, but sometimes, and in a discrete way, when the trains arrive in some part of the structure. So it is the reason why we have some unobservable events, and it is the reason why it's more complicated to think about the automations of this kind of systems.
Okay, thank you. Anything? Any more questions from the audience? Okay, that was our last paper in the session, so that concludes our session. I would like to thank all the presenters for their time and the nice presentations they prepared. And with that, we close the session. And then keep in mind that there's another session starting at, what was it, on a different time zone, I think 11. That should be the time. So check the schedule and see where you want to go. With that, have a nice day. Have a nice night to Tomás.
Thank you.
And hopefully, as I said before, we be able to see each other in person next year.
Thank you very much.
Thank you.
Thank you very
Thank
much.
you all.
Thank you, everybody.
Bye.
Bye.
Bye-bye.
Au revoir. Goodbye.